apologize, Nick. I have to take off to teach.
Okay, yeah.
So I guess we can get started. Thank you all for coming. This is our last talk of this mini workshop. So today we're very happy to have Nick Butch from the Center for Neutron Research and also University of Maryland to tell us about their work on correlated topological superconductivity in UTe2. So Nick, you have the floor.
Thank you. And thanks to the organizers for this invitation. And yeah, as we were saying, I'm looking forward to November. But this talk is, I made an attempt to make this pedagogical, and you know, you can determine at the end whether I failed or succeeded. It's a bit different actually from my standard talk. So I also hope that I don't stumble too much in the middle because the logical flow is a little different. Before I get started, I will figure out how to do this. Okay. So I want to just acknowledge collaborators, and I'm not going to read everybody's names, but you know, Sheng Ran was my postdoc at the time when all this happened. He is now faculty at Washington University in St. Louis. We work closely with JP's group at University of Maryland, and the initial measurements also, or the initial paper also had work from Yuji Furukawa's group at Ames. That was NMR stuff. We've been doing a lot of MagLab measurements, and we have a long list of collaborators. I also want to say, actually, I mean, there's a big, let's call it a competition, race, whatever. There's a lot of international interest. And so we are by no means the only people doing work on this material. Although, of course, I'll focus mostly on stuff that we've been doing and hopefully acknowledge people when it's appropriate. Okay, so this is the outline of my talk. And what I would like to talk to you about today, or the way that I structured this, is not like skipping any real parts of, you know, what we know about uranium ditelluride, but I want to just upfront give you what I call basic facts, and then dwell on, hopefully in a reasonable amount of time, 3 big questions. One is dealing with the normal state properties of uranium ditelluride, and specifically, is it ferromagnetic or close to ferromagnetic? Then what is the nature of the order parameter? So what do we know about it so far? And then finally, what can we say about high field reentrant superconductivity? Okay, so since we grow crystals, I always like to show these things. I say this every talk, but I think it's helpful to look at them. And just to, you know, remember these things came from nothing. We mix uranium and tellurium. And in this case, we use iodine as a transport agent in chemical vapor transport in sealed quartz tubes. And you get single crystals if you do it right. The scale here, let's say just on the right, is millimeter size. So these are not typical, shall we say. You know, you get a lot of small crystals and then you get some bigger ones. But this is what they look like. They're shiny. And this is what the crystal structure looks like. It's orthorhombic. So on the left, there is actually multiple unit cells. I just have that projection because, or that direction, that viewing angle, because I like to emphasize that there's a linear uranium chain structure here. And it actually coincides with the easy axis, the magnetic easy axis. The other thing is that this is a centrosymmetric structure. And on the right, I'll just show you a quick rotation if this works. And if I pause it right, let's see. Okay. The kind of motif that I want to emphasize here is that there's this uranium chain, or if you prefer, a zigzag of uranium telluriums like this. Okay, and then there is another tellurium layer here. And so there's 2 tellurium sites. This becomes important when we start talking about electronic structure. But I also want to emphasize that even though this is a 1-2 stoichiometry, this has really no relationship to transition metal dichalcogenides, which are also orthorhombic, typically in their vial phases, but you know, very different physics. So, and I apologize for those who want to talk about band structure calculations. I'm going to sort of just assert things, and then we can argue about it later if you'd like. What I'm showing you here are a combination of calculations and photo emission results from Andrew Ray's group. The work's coming, the calculations are from Gabby Kotliar and Chengjun Kang. But essentially, what ARPES tells us is that there's two highly dispersive electron bands that form a quasi 2D Fermi surface shown here. So if you took just a cut through, it looks like rectangles. Oh, we can't see your pointer. I'm sorry. Thank you for mentioning that. Let's see. Does that work here? Can you see my pointer now?
Yes.
All right. So I'm just pointing at the wrong screen. Sorry. This is screen management. All right. So here. So there are these sheets. They're not very dispersive along Z. Okay. And I'll try to avoid pointing as much as I can. So the thing about this is that many of the calculations will have this feature or will be actually way more three-dimensional. Photo emission finds an additional pocket that looks like it's 3D. And we can, sorry, without higher resolution, give me for a sec. You can maybe ascribe this feature to to things that are calculated in a different calculation. From just a basic level, I would like to sort of leave it at this. So we know that they have these dispersive bands. The question is, at low temperatures, where is the F weight? And we expect, for example, that we would have a renormalized band structure based on things that I'm going to show you soon. So that's open question experimental. Then, here we go. This is the temperature dependence of the electrical resistivity. So I just told you, oh, it looks like it's quasi 2D plus some extra stuff. And if you are familiar with heavy fermion type phenomenology, you might say, well, extra stuff should really only be relevant perhaps at low temperatures. But it turns out that if you look at the three directions, so rho A, rho B, and rho C, which correspond, so A and B are the in plane. A is, if you consider this sort of like a rectangle, A is along the uranium chains and C is out of plane. Now, quantitatively, C is about the same size as, rho C is about the same as rho B and rho A. So it's not like it's much more insulating along that direction. This fact actually led us to take a very long time, along with the natural sort of behavior of the samples, to determine. So like two things I just say here. So it doesn't look two-dimensional, but also if you're looking at the temperature dependence above about 50 Kelvin, the slope is negative for rho B and rho A. This is your sort of stereotypical heavy fermion behavior. And it's very different from just a simple metal. Okay, superconductivity. I like to show this slide, well, because now it's been 3 years since we learned about superconductivity in this material. It's helpful to me to sometimes like remind myself that it took a really long time to get the first paper published. And that wasn't until August of 2019. But these are the results. First results were actually AC susceptibility. We said, oh man, what is that? And then the zero resistance. So we know that these are hallmarks of superconductivity below about 1.6 Kelvin. So if we do then our standard, do measurements for a long time in different field orientations, you can build up the figure on the left side. It's HT2 plot. This is again from the original paper. And there are a couple things to note. One is that the upper critical field curve is very anisotropic. And but regardless of that anisotropy, in all directions, the paramagnetic limit of Pauli limit of 3 Tesla is exceeded, which suggests that you are not dealing with a spin singlet configuration. Or that means basically Zeeman energy is not somehow killing your superconducting state. And in fact, if you go along the B-axis, the superconductivity doesn't get destroyed until 35 Tesla. That's just the plot on the right that's showing you resistance data. And in the inset, I'm showing that there's also a step in the magnetization at that field. So that's not even necessarily an orbital limit that actually corresponds to There's a metamagnetic transition. So it's a change in the underlying normal state, or at least there's one that comes along for the ride. So it's more complicated than that. Okay. So what about this? Well, we don't live in a vacuum. And of course, people have been looking at ferromagnetic superconductors, especially in the heavy fermion community, for a long time. The upper critical field curve, UTe2 here on the left, shown for a different sample taken, so from a paper by Knebel and coworkers on their samples. So this is Japanese-French collaborators. You can see this reentrant superconductivity, which, so what does that mean? That means that applied field kills superconductivity and then it returns at some higher field. There is some sample dependence. So when they compared against what we had, their TC and HT2s are lower, but nonetheless, the general shape looks like those of uranium rhodium germanium and uranium cobalt germanium. The important distinction between these two different classes of materials is that the latter are actually ferromagnetic before they become superconducting, and it's not controversial that those are spin triplet systems. All right. Another thing is that this chain motif that we see in UTe2 is very similar to one that is also seen in uranium germanium 2 and uranium rhodium germanium, uranium cobalt germanium. So they're orthorhombic. You have these kind of one-dimensional chains, and the latter are again ferromagnetic. So that leads you, and one final circumstantial argument. The chemical cousins of UX2, so of UTe2, use selenium and sulfur, although they're not actually the same structure, are ferromagnetic or close to ferromagnetism. So given all these things, you might ask, what about UTe2? Where does it sit? You know, what role in the universe does it occupy? And so that's kind of where this phase diagram comes from. This is completely conceptual, with only, you know, the temperature axis having some kind of qualitative meaning. But the idea would be that UTe2, because of everything here, maybe it should be a ferromagnet, but it's not. But it is has the highest transition temperature among these types of superconductors. Okay, so let's expand on that a little bit. So UTe2 is a heavy fermion. I told you the resistivity looks like it's a heavy fermion. If you look at the specific heat, here plotted as C over T, you'll note that there's a large Sommerfeld coefficient, 120 millijoules per mole Kelvin squared. I can tell you that the low temperature resistance is quadratic. The ratio, Katawaki-Woods ratio is okay, 10 to the minus 4. Wilson ratio plotted in the upper right corner also shows that, you know, this kind of falls in the continuum of materials and it's acceptable. So it's not really a standout there. And so if I look at the temperature dependence of the magnetic susceptibility, this is, it's anisotropic, okay. The red curve is for a field along the A-axis, that's the uranium chains. And the green is the B direction, so that's perpendicular to the chains. And then blue is C, which is, let's say, perpendicular to, which we keep referring to as the planes, but that's perpendicular to the two-dimensional Fermi surfaces that we're using as a rough guide here. So the green curve shows a pretty interesting temperature dependence. It has a maximum and then curves over. This I also say is kind of stereotypical of heavy fermion behavior. The red curve, below about 10 K, there's a change in slope. But if we just do a field sweep at the lowest temperature of the squid magnetometer, 1.8 K, you don't see anything really remarkable. In fact, we can place an upper limit on any ferromagnetic ordered moment of being pretty tiny fraction. And furthermore, neutron diffraction studies down to 2.7 Kelvin have found absolutely no evidence of symmetry breaking. So we don't see anything in specific heat, don't see anything in the magnetization. So, and of course, also not in the resistance. So there aren't any indications that there is a magnetic phase transition down to this temperature. Okay, and then I wanted to dwell a tiny bit on doing the analysis of the magnetization here. part of my attempt to be slightly pedagogical. So one of the things that I wanted to point out here is that if this is an uncorrelated paramagnet, that we would expect generically to have field over temperature scaling. And that doesn't work. So you could say, well, that's probably because it's correlated, right? There, you know, this is near some kind of magnetic phase transition. So what do we do about that? So if we assume, based on everything that I've told you so far, that the magnetic phase that's close by is ferromagnetic, and we also say, well, we have to bear in mind that it's metallic, we might refer to the theory of Belitz, Kirkpatrick, and Boita on ferromagnetic quantum phase transitions. And so we can have anything from quantum critical point for a dirty system to a discontinuity for a clean system, and then the presence of wings as a function of field. And this has been seen in many materials now. It's fairly well established. But in order to try to do something with this, we want to analyze the magnetization data that we've got, and then make some statement about critical exponents, even though we don't have order. So the idea would be, let's see if we can say something about a material that looks like maybe it tries to order at 0 temperature. And just for your reference, I have like just tabulated mean field exponents, beta, gamma, delta. So beta is the temperature dependence of the order parameter. Delta is the field dependence of the order parameter. And then gamma is the temperature dependence of the susceptibility. In this case, we'd be measuring it in the disordered state. And these can be all combined into some Arrett-Noakes scaling equation. Okay, so if we just try mean field, it completely doesn't work, or rather it's unsatisfactory. I'm just showing here on the right what I would expect it to look like. So for temperatures that are above the transition, we should see curves like this. And then if we were at t = 0, we would expect to see this, or something approaching that. And that just doesn't work. So these exponents aren't quite right. So can we force it? Or what exponents could we do with a modified Arrett analysis that would give us something that appears to work? So data on the left again, and then on the right, a scaling plot. That is that comes from using exponents beta 1, gamma 0.12, and delta 1.12. And I don't want to make too big a deal about this other than to say, so even though if we can get a scaling plot to work, and this is not a scaled Arrett plot per se, that this kind of is nonsense because we can't really make contact with theory. Well, it's not quite nonsense. A guy named Butch and his advisor Maple published a paper a while ago on rhenium substituted uranium ruthenium-2 silicon-2. It's also a ferromagnetic system where you suppress the magnetism, and also has some very strange exponents. In that case, there's a trend that one can point to. But these are not, to the best of my knowledge, these don't actually have any kind of a theoretical underpinning. So there's nothing that really truly explains them.
Nick, can I interrupt you for a second?
Of course.
So I suppose, I mean, there's no reason for those exponents to work because those were for thermally induced phase transitions, right? In other words,
yes, that's right. So the universality class, well, okay, maybe I should put this a different way. These exponents are determined for a thermal phase transition. That's right.
Yeah.
And then the question about a quantum phase transition, how would that change things, or whether we are actually determining exponents that are directly addressing the quantum phase transition, right, the 0 temperature one, is a good one. But from my understanding, actually we can still, if the critical region extends far enough away from the 0 temperature transition, you should still get exponents that reflect this, I think, even in the temperature direction.
Yeah. If you don't mind, I just want to follow this up. So by now there are, presumably there are more data on the magnetization. To what extent the scaling actually is working in all different measurements of different groups?
So I don't think anybody actually has repeated this.
Mm-hmm. Okay, thank you.
Yeah, but that is a good question.
Can I ask a related question?
Yes.
So how temperature dependent is M versus H? And the reason I ask that is I'm looking at this plot, and you're plotting M over T versus H over T to something close to 1. And so it just seems like if you had a temperature independent curve, it would also move up and to the right as you cool down, if you know what I mean.
Yeah, no, you're totally right. And I mean, so basically here, just look at the plot on the left. So this is basically from 2K to 9K. And
right. So I guess I'm struggling a little bit with whether a totally temperature independent M versus H would also give you something that could masquerade as scaling.
Oh yeah. Yeah. Maybe at the end of the day, that's my point here.
Okay.
This is unusual behavior, and I'm taking a long time here to try to make contact with any type of theory, and I would argue that this is not satisfactory.
Got it. Okay, thank you.
Maybe this is backwards in a way, right? Usually you're trying to make a case for something. What I'm trying to say is that this is the analysis that's left to us. And another thing that I'd point out is if ferromagnetism, if ferromagnetism is if this is a ferromagnet, the bulk magnetization is the order parameter, and it is appropriate to at least attempt to do these kind of analyses. If I zoom in to the low temperature behavior for the magnetization along the A-axis, I mentioned that there's this change in slope around 10, but you can do another just kind of power law fit. And this is just to emphasize, again, you can call it Curie-Weiss or modified Curie-Weiss or whatever, but now it's something that's got a large susceptibility offset, okay? And the scaling itself, there are arguments from even mean field analysis that it's insufficient to just show a plot like the one on the right. And in particular, I would, if somebody were showing me this, I would want to see a bifurcation. So I really want to see something above and below an ordering transition to say, hey, you're not just, this isn't just an accident. But that's what we've got if we've got a t equals 0 transition, we're kind of limited. Okay, so if we can subtract the susceptibility from all our data, we can actually conveniently get exponents of beta equals 1, gamma equals 0.5, and delta equals 1.5. And you can say, well, that's kind of crazy. What is that about? Well, those actually do correspond to the BKV theory. And so that's about, my statement is that that's about as good as we can do. And this theory, or these exponents have actually been observed for magnetic order in this medium entropy alloy. But yeah, a big problem with the application of this, even if you wanted to take it seriously, is that uranium ditelluride is not obviously in that limit. It's not really strongly disordered. So what does that say about this material? So this, let me propose then, this I think is ripe for theory, for some additional insight into what might be going on. Okay, so it's not the only probe we've got. There's MuSR, and full disclosure, the expectation for the MuSR experiment was originally to see if there were signatures of time reversal symmetry breaking in the superconducting state. But it turns out that Jeff Saulnier's group found that there's really strong spin fluctuations at low temperature. In fact, they're so strong that they can mask any potential time reversal symmetry breaking in the superconducting state. So if you just look at the temperature dependence, there is no kink at 1.6 K. It extends to much higher temperature. Another salient point is that the temperature dependence of 1 over T1 is consistent with three-dimensional itinerant ferromagnetic quantum critical point from SCR theory anyway. And then so that's this plot on the right. And then at low temperatures, there's a deviation from that temperature dependence, which we can interpret as perhaps being due to the inaccuracy of the SCR model when you get to low temperatures. So, okay. And then there, of course, has been neutron scattering, inelastic scattering work done by the Rice group. Pengsheng's still around, so he can comment if he wishes. And the surprise is that there is scattering seen at finite momentum transfer. So you want to talk about it looking like there's antiferromagnetic like spin excitations. So the question is, which is more important, or perhaps they're equally important to the both the superconductivity and perhaps even the normal state. And I have this comment about confirmation bias, just like, you know, try to keep true to or being honest about this. If I want to talk about spin triplet superconductivity, my tendency is to go toward ferromagnetic interactions because they are associated with spin triplet pairing states. And in fact, you can make some generic statements about ferromagnetic superconductors and topology. And this is just coming from a paper from Sao and Tawari. I'll read it to you basically three-dimensional. So the equal spin pairing state, Cooper pairs condense forming these parameters, which are decoupled in the spin sector, and that these 3D systems should generically support topologically protected surface states. So that's all the rage nowadays. And so question number 2 is uranium ditelluride, a topological superconductor? Let's just make a list of demands, experimental demands, in order to at least make the case for this. You want chiral surface states, time reversal symmetry breaking, and a 2-component order parameter from which all this stuff comes. It's not entirely just an experimental exercise now. There have been many suggestions from theory regarding what kind of order parameters might actually be found in this material. I'm listing the ones that I believe all of them are topological in some sense, okay? And then in the bottom is just a little phase diagram from the Shishidu paper showing the how the temperature and field dependence of, you know, multi-component order parameter might look for a certain direction. Okay. So point number 1, we want surface states. And indeed, these have been delivered by the Madhavan group at Urbana, so STM work. I'm actually skipping a great deal of interesting stuff in their paper to focus on just the surface part. And here what I want to emphasize is that there are these up and down step edges that are observed. Interestingly, they are really long in these samples when they see them. And the statement is that regardless of where you are in the sample, there's an orientation to the up and down edges. And in any case, when you find the up edge or the down edge here, the called P or N type, you will always have an orange or a blue spectrum, as shown on the bottom, which are asymmetric, but they are on the energy scale of the superconductivity. So it's a very small energy scale. I think the detail of the detailed shape is not really well understood, but they are asymmetric and opposite each other, and they form always on opposite faces or on opposite steps. This is the definition of chirality. So there you go, checkbox number 1.
So Nick, can I ask a question?
Of course.
Yeah, so there are proposals for, if this is a Weyl topological superconductor, for the orientation of the Weyl nodes. And in the simplest picture of a Weyl topological superconductor, like if you have just 2 nodes, then yeah, you have chiral states, but it's not a 2-dimensional system. It translates into sheets of current that are running along the surface. And you would expect a constant density of states associated with these sheets, chiral sheets of current. So looking at this data, what crystal surface are they looking at here? I mean, would you expect to see a chiral surface current flowing across this top surface? Why is it only along step edges?
Yeah, I don't. First of all, I cannot explain this sufficiently well, and I'm not really sure whether the tie-in. So I think at this point, the relationship between the proposed order parameters and the chiral states and why it shows up this way. I mean, I could not explain it to you. I think to to a degree that you would find satisfactory.
I mean, I guess the zeroth order question is just, you know, if the vial, so in order to see chiral states, you're supposed to be looking at an interface where the vial nodes are separated in momentum space rather than, like, say, head on. So
right.
That particular surface where they only see it along the edges but not in the big mesa, is that, do you know if that is a surface where the two vial nodes would be head on?
Okay, yeah, let me tell you what I do know. So we know that this material cleaves along the 011 direction. And so if you look closely, you can see the orientations of these steps as determined by the Urbana group. So from a theory standpoint, I'll refer to conversations and papers from Daniel Achterberg. And given, let's say, our favorite proposed order parameter or symmetry anyway, B3U plus IB2U, the vial nodes might live either on KX equals 0 or KY equals 0. But I believe that there is some flexibility in terms of where exactly they are. And so I think that is consistent with potentially there being these, that is consistent with these modes existing. So I think
so meaning that if you could somehow measure down the actual interface and not just close to it, you would have a sheet of chiral states, I guess.
I would, yeah, I think that's the expectation. When will we get to that day? This material, you know, behaves the way it does. And so this is actually the easiest cleave axis or easiest cleave direction. And, you know, doing controlled studies as you're talking about are going to require a bit more control than we have currently.
Sure, thanks.
So, all right, then points number 2 and number 3. How do you find evidence for time reversal symmetry breaking, especially if mu-SR can't? Well, another thing you can do is an optical Kerr rotation experiment, especially if your name is Kapitolnik. And indeed, Stanford group has found evidence for finite optical Kerr effect. And I showed you earlier a single jump in the specific heat, but if you do a more careful experiment, that is smaller temperature steps, for example, in your calorimetry, you'll find what we're showing here on the right, which is that there are actually always 2 jumps. So this jump actually is really 2 transitions. And I'll talk a little bit about that in the next couple slides. But I'm going to skip these kind of quickly because I wanted to also say, hey, there's other evidence that is, you know, falls into a traditional pool of evidence for spin triplet pairing. One is NMR. Just, you know, a reminder that this has been famously used to demonstrate triplet superconductivity in strontium ruthenate, and then we can talk about that later if you'd like. But in this case anyway, we started off with powder NMR, don't see any change in the night shift through TC, and single crystal measurements done in Japan in the Ishida group have basically corroborated this. Although they do see small shifts, it's way too tiny for any kind of singlet pairing state. Second, microwave penetration depth experiments, which I'm not going to dwell on here, I'm just going to flash them at you, are also consistent with a point node structure and in fact some pretty weird real part of the conductivity behavior below TC. But I wanted to focus on the specific heat. So this is old, I'm sorry, maybe I didn't show this before, but here we go. So I showed you the two transitions before I showed you the first one. I apologize for that. This is from the paper, and one thing about it, it's, let's say, easy to read off, and you can take with a grain of salt, is that the temperature dependence doesn't look exponential. So already was, you know, consistent with there being some kind of nodal behavior. But in particular, if one extrapolates to 0, there is always a really large residual term, which is about half of the normal state term. So it looks like to you know, people who want to find spin triplet superconductivity, perhaps a state where only half of the Fermi surface is paired. And this idea is inspired by the A1 phase in helium-3, which is, of course, what we keep going back to, you know, as the archetype for spin-triplet, in this case, superfluidity. And the A1 phase, just to remind you, lives in finite field, but it is really, it's an equal spin pairing state where it's considered half of the A phase, and it's non-unitary. It breaks time reversal symmetry breaking, but of course it's in field. So I was looking around and I said, well, actually, we're going to do a comparison of the specific heat. Main problem with that entirely is that it lives over such a narrow range of parameters that you're never going to get a low temperature limiting behavior in this thing. So can't do that. Another point that I would like to raise is a comparison, again, back to the other materials that are ferromagnetic superconductors. You might say, how does UTe2 compare? Well, at least from this review article by Mineyev, it seems like there's a correlation between the large residual terms and, excuse me, the ordered moment. UTe2 having no ordered moment doesn't follow this trend and still actually has a fairly large, a very large residual term. So we can't really look to them for guidance either. And to carry on with this trend of like, hey, there's something wrong, we don't understand, the thermal conductivity measured by JP's group, well, two things. One is that the field dependence that I'm showing here on the left is consistent with nodal behavior, unconventional superconductivity. But I want to raise two additional points. One is I'm showing in the figure on the right, in this case, an extension beyond our earlier measurements. So the C over T down to lower temperatures, you'll notice that there is actually an uptick here, right at the lowest temperatures. And one of the problems that if you read faster than I talk is that in the thermal conductivity, there's a negligible low temperature term. It actually basically extrapolates to zero. And the thermal conductivity is supposed to be proportional to the specific heat. And so if we expected to have half of a Fermi surface left over, we would expect that it would actually still be carrying some entropy. And that doesn't seem to be the case. And so in this figure, there's a construction, albeit not motivated or not tied down to any sort of theoretical underpinnings, about what you would need to subtract in order to just get this resulting red curve where the electronic specific heat goes to zero, as you would expect in, let's say, a conventional case. So basically the statement is, if we want to get rid of that stuff, we have to assign it to a local or localized degree of freedom of some sort. And that's a question mark. What is that? It's, as far as we can tell, for example, it's not nuclear Schottky anomalies or something like this. All right, now I also want to mention that a contentious point is the specific heat jump. I said there's two. Not everybody agrees. Well, for one thing, if you make the material by the flux growth technique, you don't get any superconductivity at all. In that case, we can at least correlate that with very high residual resistivity or relatively high residual resistivity and say, okay, maybe that's just due to disorder. But the mechanism is not actually well understood. But up until fairly recently, the University of Maryland was the only group that actually identified a double transition. And just as an aside, I want to just remind everybody that sample quality in some way has been sort of a theme here with spin triplet superconductivity, including strontium ruthenate. Again, you know, regardless of whether it's a spin triplet system or not. If you make samples that aren't so good, you might not even see a superconducting transition. And this is definitely true for the 214. It's also true for uranium, rhodium, germanium, and kind of to a lesser extent for uranium, cobalt, germanium. But kind of around March meeting, the Los Alamos group posted something to archive with specific heat showing also double transition. So, you know, it's not just the funny air in College Park that's giving us two superconducting transitions. It's, we at least know that if you make the samples a certain way, that you will consistently get this double transition. But again, the underlying cause of this and the relationship again to the order parameter is under investigation still. So I want to throw another fact at you, and that's that under pressure, nobody disagrees that there's more than one superconducting phase. It was a double negative, I guess, right? So there is broad agreement that there's more than one superconducting phase. From the initial studies, it looked like 2. If you look more carefully, there might even be 4, okay? And the question is, of course, if there's 2 under pressure, why doesn't that extrapolate to 2 at ambient? And on the rightmost, in the rightmost panel, so this is data from the Los Alamos group, it kind of looks like it really does extrapolate back, but this is, you know, an open question again. So especially for the groups that only see one superconducting transition at ambient, how does this connect to their data under pressure? All right, and with the time remaining, I'm going to turn to the last question, question 3. What about the high field phase diagram? And it's a little unfair because those of you who aren't familiar with this, I just showed you this for the first time. But this is a 0 field phase diagram, a magnetic field on the vertical axis and direction, so field orientation on the bottom. And if we're talking about that thing I mentioned a long time ago, this 35 Tesla phase, that's the low field phase, okay? It exists over a very narrow angular window about the crystallographic B axis. And if we're to assign sort of a qualitative label to the lower temperature stuff, so the lower field superconductivity looks kind of 3D. Then you get towards B, there's this narrow finger over which it extends up to 35 Tesla, and above that, reminding you that there's a magnetic transition. So there's this, what we're calling a field polarized pink phase. And then what I've labeled Lazarus superconductivity, and I thank the Mag Lab for that label. There is another superconducting phase that lives between 40 Tesla, actually higher than 60. We're not really sure exactly how high it goes, but that's kind of what it looks like. There's a bubble on the other side of the magnetic transition. And just to give you a sense of scale, right? Here's a plot of, you know, various HC2s, so upper critical fields for different families of superconductors. The biggest ones, cuprates on the right. Then kind of in the middle, you've got transition temperatures falling in the 50s for the iron superconductors, and they still go pretty big. Uranium ditelluride is a delta function on this plot. And the field scales here are pretty remarkable for something with such a low TC. Okay, so let's rotate our magnetic field to where this yellow line is, so this direction, and just perform a resistance experiment here for a couple different angles through here. You'll notice that you've got superconductivity at low field, goes to the normal state and becomes superconducting again. Okay, so again, that's just the very definition of reentrant superconductivity. And we can do more than that. We can map these out. So basically breaking up that angle into vector components, H along B, H along C. On the left side, that's resistance data. On the right side, this is diode oscillator data. So high frequency, kind of, you want to call it skin depth measurements or something like that. Very complementary. They show you that this pocket exists in a range of angles, as I already showed you in the phase diagram. If we look at the temperature dependence of this pocket, so shown here again, same two measurement techniques as a function of now temperature and field. It looks like they extrapolate down to 1.6 here for the resistance. A little bit less certain what's going on here. Well, rather the extrapolation doesn't look so good, although the color plot also seems to show the same temperature scale. So again, that means that this is something, if, let's just say, other examples of high field superconductivity don't necessarily have the same TC. They're usually lower, or often are lower. So this is showing you that, or saying something about the energy scale of this high field pairing state. So what mechanism could possibly stabilize this? And I'm just going to go through a couple, because it's not like there's a really long list. One is a fairly old and established one, the Jaccarino-Peter effect, in which there is a compensation with an external exchange field that opposes your applied field. And that's shown here in the diagram on the left. So if you just look at the bottom, well, this is the sum of the applied and exchange fields. And if you have some kind of limit, you can imagine a situation where the exchange where you're dipping from superconducting into normal state, back to superconducting, and then finally into normal state. And this mechanism is responsible for reentrant superconductivity in Chevrel phases from a long time ago, and also things that are still being studied, organic superconductors. But this, you know, the building blocks of this kind of effect aren't really necessarily evident in uranium ditelluride. So what else could we talk about? I love this paper from Tosanovich, resultant Jing. This is on a very high magnetic field superconductivity, discussing Landau level superconductivity essentially. So when you're in the quantum limit, to read this, so there's no diamagnetic pair breaking, and the transition temperature can actually be enhanced by the field. So, and moreover, this kind of state could exist in principle, even if superconductivity isn't the zero field ground state. And if we'd like to entertain this idea, we have to ask the question, is uranium ditelluride in the quantum limit at 45 Tesla? And there's no evidence directly yet that that's true. In fact, actually, we don't have any published quantum oscillations data or anything like that at this point. And we expect that the Fermi surfaces are pretty big, right? So what else can one say? Well, there are even generic arguments about so lower dimensional superconductivity. In particular, so I'm quoting here a paper from Andrei Lebed, who actually wrote an article particularly specific to uranium ditelluride, that if you've got a quasi 2D superconductor, you know, at high enough magnetic fields, the electron motion between the planes is reduced. Eventually, your cyclotron motion is, you know, it's smaller than the spacing, and then this can occur for any in-plane anisotropic electron spectrum and for any equal spin in-plane electron-electron interaction. So it's kind of a generic argument. This picture on the left is also, so in this case, temperature vertical and field horizontal, showing you essentially kind of what we see, right? So I am not telling you that any of these is directly the answer. We need to find a way to corroborate some of these, you know, especially the latter argument. And you could discuss about whether, again, is UTe2 really low dimensional? Okay, and finally, I just want to point out that even under pressure, so we eventually destroy the superconductivity and come to a magnetically ordered state. But even in the presence of that magnetic order, with the application of a little bit of field, so here's pressure axis, and this blue phase here lives on the boundary, on the field boundary of what I'm labeling here FM, but we haven't really determined the order parameter here. So it's a magnetic order. And if you look at these plots, these are HC2 plots sort of on their side. There's a bubble of superconductivity, excuse me, below about 10 Tesla that seems to live on the edge here. So there's more reentrant superconductivity in this material. It's kind of everywhere. Okay, and now I'm going to finish up with answering these questions that I posed. And I'll, of course, caveat is that these are tentative answers. So I hope I've convinced you that UTe2, there's at least evidence that it's an incipient ferromagnet. There's also evidence that there are other interactions that are important. That there is evidence that this is a chiral superconductor that breaks time reversal symmetry. And that at least as a leading candidate for what might be going on at high fields, dimensionality may play an important role. But of course, all of these are subject to further investigation that is, of course, necessary. So I really appreciate that people were asking questions in the middle, and I guess this is a good time to stop and ask you for more. So thank you for your attention.
Thank you very much, Nick, for this very comprehensive talk. Any questions from the audience? So I guess I can, while we're waiting for questions. So Nick, so I remember in the beginning, you mentioned that this material is not very low dimensional based on the ratio of the resistivity. So what do you mean? So for the last point, what could you elaborate a little bit? What do you mean by this? low dimensionality stabilizing the high field?
Well, okay, so maybe I should say that I'm not, let's say, in my limited understanding of what can happen at high field, there really isn't a very long list of possible mechanisms that can stabilize a superconductor, especially once you pass what you think should be the orbital limit. So most of them have something to do with low dimensionality. And because because the currents can't flow in some way. And so we can, I would say that that's accepted until somebody comes up with another mechanism that could somehow suppress an orbital limit. But about the intrinsic dimensionality of the system, where I hand waved or perhaps insulted people by saying, hey, it looks like it's just a bunch of rectangular sheets plus some extra stuff that we don't understand. We're confident in the rectangular part because the bands that those Fermi surfaces derive from are very high in energy and they're very dispersive. So they're pretty easy to see. What we're not confident at all about is what's going on near the Fermi level, because that hasn't really been well resolved by photo emission. And for some calculations, that's a hard thing to do at low temperature as well. It doesn't mean that there isn't F weight there, but maybe the statement I should make is, I think the F electrons are integral to the three-dimensionality of the system. There's a question in my mind, what exactly that looks like, and also what the temperature dependence should be. Naively, I expected that because this is heavy fermion temperature dependence along the easy directions to measure, that perhaps there's a strong temperature dependence in the C-axis. And that seems to not really be true. That means that basically either the F electrons are, well, what's the best way to put this? There's always a three-dimensional Fermi surface or something that is good enough, right? There isn't really strong inner layer scattering. Then you can ask me, what does that have to do with the high field behavior? And I don't know how to get from a fairly isotropic low field resistivity to a quasi 2D state at high field. But that's something that I hope that future experiments will shed light on.
Okay, thank you. Now it's quite a number. I think it was Doug who raised your hand first. Doug?
Real quick question. Going back to very early in the talk. So those resistivity numbers are quite high on the scale of things. How close is this system to basically the Jaffe-Regel limit?
Oh, okay. Yeah. Let's see. I don't think we exceed it. And I would also say, as far as like high goes, I don't think that, I mean, they're not really big, like, generally compared to other heavy fermion compounds. So,
okay.
Yeah.
Yeah, I may just not be well calibrated for the heavy fermions. Thanks.
But maybe a better way to think about it, there's a lot of scattering, but it's not necessarily like, we're not necessarily close to some localization. Yeah.
I see a number of hands. I may get the orders wrong, but the next one I see is N the Visar.
Yes, indeed, I had a question. Thank you, Nick, for the nice presentation. So I also had a question about your resistivity data. Mm-hmm. So one of the first slides. So for one of the directions, there is a pronounced peak, or the pronounced maximum.
Right. Let's see.
You did not comment on it. It looks like there is a kind of a phase transition there.
Right. Well,
so do you see that in other properties, or so? What is it?
What is it? Is a great question. That's a fantastic question, in fact. So let's see, what am I doing?
Yeah, still a few back. Further.
Yeah, here we go.
Weird.
All right, right at the beginning. Yeah, quite right. So we saw behavior like this in one of our early pressure experiments, and we weren't really sure exactly about the current direction. So I'm going to say a couple things about this. So first thing is that it took a while to get this. Not just because we expected that rho C was going to be large, much larger, and that anisotropy and kind of mistakes in orientation could screw things up. But Yusuk, who is the first author on this, took a really long time to be able to separate out the different contributions. So for the details of how to do this, I would refer to you to this archive paper. Now, so you mentioned the peak. This peak is, I call it a robust feature. We've seen indications of this in a long time and didn't quite understand it. We're also worried about, for example, are contacts bad and things of this nature. The change in behavior, this 50 Kelvin temperature scale, is one that's also corresponds to what happens in the magnetic susceptibility. There's another kink in the magnetic susceptibility, as I mentioned, around 10. And so this peak here is around kind of 10 or 12 Kelvin, or maybe 15 if you want. And there are data also from thermal expansion that suggests that there might be something going on around in that temperature range. And although it's a sharp feature here, there is nothing that we can point to in the key capacity, for example, that says, hey, this is a phase transition. So is it a crossover? Yes, maybe. What is its relationship to any putative, like heavy fermion renormalization? I'm not sure, because it kind of seems to fall into the same temperature range. Separate phenomenon or tied to it, I can't say definitively. But,
is it also sample dependent, or is this?
To the best of my knowledge, maybe the magnitude is, but you know, when you're talking about a transport experiment, these have been difficult to quantify. So, you know, questions could always be about misalignment or perhaps contact quality. So I can't really speak to the statistics of that yet.
Okay, thank you.
The next, I think, is what's Peter Hirschfeld. Peter?
Hi, Nick. Very nice talk. I have a question about the low temperature thermal conductivity that you showed. I have a recollection of hearing somebody from your group, I think, at the March meeting, doing an analysis of the relative contributions of the electrons and the phonons, and that in my head, at least, the phonons were expected to dominate down to pretty low temperatures. And so my question is, when you show these extrapolated data, has a large T cubed or some phonon contribution been subtracted from these data in order to get the extrapolated electronic part?
Yeah, these, I believe, yes. So these are the electronic part of the data. Let's see. So you're asking relatively large.
Well, I'm saying if you have to subtract a huge number, which
you're asking about the error bars, essentially. Yeah.
Yeah.
So you know, off the top of my head, I can't answer your question honestly. I don't think it's large. In other words, I don't think that there is a lot of slop in that subtraction.
Nick, JP says in the chat, not for edge dependence plot.
Oh, okay. There you go.
Sorry, I didn't hear that. What was that?
So JP says that there isn't as, wait, actually, I'm not sure what he means by that. That it wasn't subtracted for the H dependence plot?
Well, he's here. JP, maybe.
No, there's no subtraction. There's
so this is just the value at the lowest measurement temperature then? Or
this is extrapolated to zero temperature.
Extrapolated by a linear extrapolation, I assume, right?
Yeah, it's fairly linear. I mean, I don't have the data handy, but you can look at the paper and see.
Yeah, okay. All right, thanks.
It's basically linear. Yeah.
Thanks.
It's pretty clear what it is.
Next one, let's Henry.
Yes, nice talk, but complicated system. I was wondering the results on the susceptibility, which is found in the normal state, which is very anisotropic. And so you have a large enhancement of the susceptibility in one direction. Do you explain that by a ferromagnetic tendency, Ising-like or something like that?
Yeah, that's a, I wanted, that is, yes, exactly how I would expect to describe it. I don't, again, based on the fact that the crystal structure consists of these uranium chains, right? So there's already an anisotropy built into the crystal. It's, I guess, not a leap to imagine then that is responsible ultimately for this for this anisotropy. And then my bias is, of course, to say this looks like the ferromagnetic other materials, and therefore, if I like a scenario in which we're close to ferromagnetism but not quite there, that would be the direction that that we would expect the order to ultimately occur along. So the A direction, but that's how I think about it. Yeah.
The other question which could be connected to that is what happens to the night shift in NMR. You mentioned that there was no, or at least only a very weak change of spin shift below.
Yeah. So for this direction, they're not capable. They can't. Gosh, I'm not sure if I'm out of date now, but it was difficult to measure the NMR signal along the A direction.
Ah, okay.
Relaxation times, yeah.
Because big shift and maybe small very short relaxation time, yes.
Yeah.
Because that would be interesting to see whether this spin susceptibility is affected or not when you enter into the superconducting state there.
Yes.
I am a little bit, since the story of strontium retinate happened on the NMR experiments, one has to be a little bit skeptical about what can be said by NMR. I am not against NMR, of course, but one has to be sure of what is done experimentally. I didn't follow what happened there, but
so what is the field direction that NMR shows that there's not much of change?
I don't know. He showed.
Which material are you talking about for here?
Yes. Yeah.
If it's been measured, at least along B and C.
Okay. Thank
you. In
yeah.
B and C, but the problem is always which is the reduction of the shift. You know that you have to know whether you have an orbital contribution to the shift when you go to T equals 0. So it's always difficult to be sure unless in a case like the A direction in which you have a large spin susceptibility, you would expect, here you have a reference because you can get the hyperfine coupling by scaling the shift in the normal state with the temperature dependence. But if not, I don't know how you would do. You see, so when you have a large T dependence of the susceptibility in the normal state, you can get the hyperfine coupling by measuring the shift versus temperature in the normal state. So then you can see which fraction of the shift is killed when you enter a superconducting state. But if they cannot measure it in this direction, it's a problem, but they should be able to measure it. Why is it impossible? Maybe short relaxation time, you say, okay.
So I will, at least this time, refer you to these excellent papers, both of them listed here.
Okay, I'll have a look.
First author. Yeah, I mean, I was going to say, fortunately, this is not the only piece of evidence that we rely upon to argue for a spin triplet.
Yeah, okay.
Right, or a pairing state.
Suka Passion? Suka?
Yes, hi. Thanks for the nice talk. So I have a question on the anisotropies. So you gave the impression that somehow the A direction is the heavy fermion direction. So do you see that in the A coefficient of the resistivity? Is it any different from A, B, C?
Well, I mean, the short answer is yes, but I'm not actually claiming that the heavy fermion state is really anisotropic.
Well, but can we see curves of resistivity along A, B, and C with A square, with T square fits and get a feeling for that?
Yeah, they do exist. I don't have them in this presentation, excuse me. I would refer you to this, this archive posting.
And you say they are the same or they are different?
I mean, the absolute values are obviously different. I don't remember what the off the top.
No, the A coefficient. I'm not talking about resistivity, absolute value.
Okay.
What's the A coefficient?
I don't remember them off the top of my head. I don't believe that they are that. Yeah. Okay. JP said they're the same within a factor of 2.
So and then
different.
Okay. So I'm confused. Then you should say that all 3 directions are in the same way heavy fermion, right? So what does it mean that?
Well,
why do you assign the resistivity along one direction as heavy fermion-like and not along all 3? I mean, that's confusing. Okay. Just because it has this funny little shape there, but
yeah, okay, I agree. That is confusing. I'm going to restate it. If I just look at the resistivity curve, either rho A or rho B, okay, those, to me, again, this is a qualitative statement. They look like what I would generically expect of a heavy fermion system. There's many similarities. I don't know if we can agree on that. You can say, okay, there's some that don't look like that. But there's a clear negative slope at high temperature, and then it curves over, and then it goes to fermi-liquid behavior at low temperature. Rho C is actually fairly recent in terms of our, let's just say, how confident we are in its details. I am not saying that rho C is not a heavy fermion resistivity, but certainly it's got a positive slope. And then as Anya pointed out, it's got this, funny peak shape, which, what is that? What exactly is that due to? So I apologize if I gave the impression that the heavy fermion state is somehow anisotropic.
Okay, so maybe I just misunderstood it. So it's not the case and you didn't want to claim that.
I didn't want to say that.
Okay, sorry. Yeah, I have one other question. Do you have any information on the charge carrier concentration from Hall effect or something?
Well, yeah, that's inconclusive right now, I would say. So both the photo.
So is there strong anomalous Hall stuff because of the ferromagnetic fluctuations or something?
The Hall data are kind of weird, and I don't know that I'm trying to remember if anything's even published. So that's a work in progress right now, and I cannot answer that question specifically about an anomalous contribution with any confidence at all.
Okay, thank you. Thank you very much.
I believe the last question is from Han Zhu.
Oh, hi. Thank you very much. Very curious if there's any evidence in the system that you see domains. For example, the STM work seems to have, if they all have the same character for different edges, then it's all the same domain. But the transport measurement, will it be possible to see any such evidence, whether it's a single domain structure or actually contain multiple domains, or if that actually matters?
You mean, and specifically for the superconductivity?
Yes, that's correct.
Yeah.
The older from.
So, yeah, there is, and I'm not sure whether this is in the publications. The STM data, to the best of, I'm not actually sure whether there's any indication of domains there. And it's especially from the way that I presented it, yeah, you're right. It doesn't look like that. There are potentially indications from some other measurements. And I don't remember right now what in the literature we exactly say, but you can imagine, for example, that the Kerr effect might be sensitive to something like that. So no, but nothing definitive at all.
Got it. I see. Because if the STM already sees that the domain is pretty large, then for sure a Kerr effect would be very good way to tell that. Thanks very much, Nick.
I guess a final question from Simil.
Thanks, me. So Nick, I have a short question, comment and a short question. So the comment is that this Kirkpatrick, Barrett's, and Thomas Voigt analysis that really is restricted to the purely alternate magnetism limit, in which case you really need a disorder or some other special features for second order quantum phase transitions in the ferromagnetic metallic systems. But in the strong correlate limit, there are various theoretical and experimental indications that inherently you can have second order or close to second order phase transitions at zero temperature that could promote quantum criticality. So it seems to me that it would still be interesting to keep that in mind, that it's actually intrinsic feature. And so if I can turn that around and to ask you, what do you have some further experimental evidence beyond the magnetization versus the field temperature scaling that is suggestive of quantum criticality in a normal state or not?
So the MuSR data that I showed from Jeff Saunier, I think are probably, I gotta go find it again. Sorry, I'm somewhat slow at this. Here we go. Mm-hmm. Right, so we can ask, you know, what does this power law behavior in MuSR tell us? And how literally should we take SCR theory, especially if we're talking about a different type of, you know, critical theory. I guess my statement so far is, and if you were asking of whether I've got neutron data about for ferromagnetic fluctuations or something like that, I don't have anything that indicates scaling of any sort that I'm hiding.
What about NMR relaxation rate?
NMR, right. So NMR, as I mentioned, I believe in the normal state is still not measurable easily along the A axis.
No, but just along B and C. Oh, I see. So you because of magnetic anisotropy,
right. Magnetic anisotropy is important here. The MuSR data here also, if I remember correctly, were measured on a powder or powdered sample. Or rather, let's say polycrystalline sample, because just to get enough mass. Mm-hmm. So I don't think we've got direction dependence here.
But actually, if I measure NMR relaxation rate for field along B and C, I should pick up the contribution to 1 over T1 from the magnetic fluctuations along A.
Yeah, so the A statement that I can make, I think with some confidence, is that we know that there are strong magnetic fluctuations. Mm-hmm. That extend above the superconducting transition temperature, and as I mentioned from this this slide, that they dominate any signal that one might see. And the reason I can say that is because Jeff can compare, for example, just sort of the amplitude to what he would expect to see in a system where there aren't strong magnetic fluctuations, but there is time reversal symmetry breaking at the superconducting transition. Mm-hmm. So these are very strong.
Okay. Okay, it's still encouraging, so thank you.
Well, yeah.
I don't see any other, oh, there's a comment from Joanna. Do you want to just say out loud, Joanna? So I'll read it there, okay. So she says, there's a peak in one orientation of R versus T in cerium, rhodium, indium-5 due to spatial inhomogeneity in the superconducting state through TC. Is there a chance something similar happening to give the peak in rho C here?
Yeah, that's a really good point. We don't know, right? Not going to necessarily invoke a two-fluid model here or anything like that, but it's quite reasonable to expect that the complexities of a crossover from what I'm assuming still is a high temperature, let's say uncorrelated state to the low temperature Fermi liquid it's got some interesting features going on there. And that, you know, we don't know the electronic structure just yet completely. So it's quite possible that there's something going on. It's also quite possible that magnetic fluctuations have, you know, this stuff that I'm talking about at low temperature also plays a role there. So, but as far as I can tell, there isn't no sign that this is actually a thermodynamic phase transition, right? So it would be a crossover to something.
And with that, I guess we should thank Nick very much for your time and, and this great talk.
It was my pleasure.
Thank you all for tuning in. Jamel, you want to say a few words?
I think we're done. We hope to see many of you in November.
Thank you, everyone.